This lesson is about confidence intervals for proportions. And before we get to what that means, let's examine the following question. Suppose we wanted to know what proportion or percentage, essentially, of college students are parents. Well, we can't ask every single college student to find this out. In other words, we can't ascertain the value of P, the true proportion, because it's simply impractical to survey that many people. So what we do is we conduct a small sample. So suppose we surveyed 500 college students, and suppose that 140 of them said, yes, I'm a parent, and the rest said no. Well, we could divide the number of yeses by the total surveyed. That would give us the percentage of those in our survey who were parents and had a child. We call that P hat, or the sample proportion. In this context, we also call it a point estimate, because it's 1 point on a number line, 28%, and that represents what we think the larger population proportion might be. But of course, we can't know that for sure, because as we know, samples vary. What we really would like to do in a case like this is get something called a confidence interval. A confidence interval would be a statement that said something like, the true proportion is between this and that number. Now we have a hunch that it's got to be near 28%, but again, because samples vary, we don't know that that is exactly accurate. So it might be slightly lower than 28%, or the true proportion who are parents might be higher than 28%. But if we can make a between statement like this, we will have what statisticians call a confidence interval. In order to compute this, we've invented something called standard error. And standard error is sort of how far off we might expect our survey to be from the true population proportion. In other words, our standard error is a calculation of how far P hat and P might be apart from one another. By the way, looking at the numbers under the radical here, you can see that the 28% is our percent that said yes, the 500 was our sample size, and the 72% was the proportion in our survey who said, no, I'm not a parent or don't have a child. There's a more general formula for that here, which we'll get to later. But in this particular case, the standard error works out to about 2%. And that roughly means that it wouldn't be unusual if our 28% estimate of the true population proportion were off by maybe 2% one way or the other. So what we could do is take that point estimate, we could add 2% to it, or subtract 2% from it, and it wouldn't be unreasonable to make an estimate or a statement that somewhere in this range, between 26% and 30% of college students are parents. But here's a problem. Statisticians have found that when you routinely make statements like this, when you use one standard error as your guide to make confidence intervals, and when you make statements like the one you see at the bottom of this video, it turns out we've proved both theoretically and in practice that your confidence interval only contains the true proportion about 68% of the time. And while that's not horrible, we also don't want to engage ourselves in a statistical practice where we're only correct 68% of the time. That's not really good enough for scientific standards in most cases. So what statisticians decided to do then was say, okay, well, maybe instead of going one standard error away from the point estimate, why don't we go 2 standard errors away, either above or below our point estimate? And this turned out to be a pretty good idea, because what statisticians discovered and proved theoretically is that if this is your practice and you do this repeatedly, survey after survey after survey, that your confidence interval, in this case the statement that the percentage we're looking for is between 24 and 32, that this confidence interval will contain the true population proportion 95% of the time, which isn't bad at all. And this is, in some sense, can be a standard practice to compute your standard error and go 2 standard errors either direction from your point estimate to get your range or confidence interval of where you think the true proportion might be. Statisticians wondered what would happen if they went a step further and asked, what if we went 3 standard errors to the right and 3 standard errors to the left of our point estimate? Well, that turned out to have a fabulous reliability, in the sense that when this is done repeatedly, when this is your method of operation, when you always go 3 standard errors in either direction from your survey, the good news is when you make estimates like that, those estimates contain the true population proportion 99.7% of the time, which sounds great. Wouldn't you rather be correct 99.7% of the time as opposed to, say, 95% of the time, as we saw in the previous chart? Well, yes and no. The price that you pay for that high percentage accuracy is that your confidence interval gets very wide. And if you look at the statement at the bottom, to claim that the proportion of college students who are parents is somewhere between 22 and 34, while highly likely to be accurate, is such a wide interval that it isn't really that useful, because it doesn't really narrow down the parameter that we're looking for. And so, let's summarize what we've thought of thus far. When we use 1 standard error as our measurement device, we've created something called a 68% confidence interval, which is fine, but not great. When we use 2 standard errors, we've produced a range of values that is 95% likely to contain our true population proportion. And if we go 3 standard errors out, we have what's called a 99.7% confidence interval. Now, it turns out, as you may have guessed, 68% confidence intervals are rare, because it's not a high enough confidence for us to be able to feel good about the generalization that we're making from our survey. But 99.7% confidence intervals are also rare, because while highly likely to be accurate, they provide such a wide range of values that they're not particularly useful. But what if we wanted an 85% confidence interval? Well, then wouldn't that come from somewhere between 1 standard error and 2 standard errors away from our point estimate? Maybe it's 1.5 standard errors. Well, it turns out that's close, but it turns out to be 1.4 standard errors away from the point estimate. And where that number came from will be the subject pretty soon in this video. You'll hold on to that thought. Or what if I wanted a 98% confidence interval? In other words, what if I wanted a process that 98% of the time would capture the true population proportion, which we of course can't really know? Well, maybe that's 2.5 standard errors away. Well, it turns out it's not 2.5, it's 2.3. And again, where these decimals are coming from, we're definitely getting to here in just a moment. But even our 95% confidence interval, which we discussed as being 2 standard errors away, isn't really exactly 2. It turns out it's 1.96 standard errors away. And so what we need is a method where we can figure out, based on our confidence interval, how many standard errors we need to allow ourselves to go to the right and left of our. Now, so far, I haven't taught you specifically how to do a confidence interval problem, but I have given you a sense of some of the vocabulary and the ideas behind what they are. Let's revisit our original problem, and I'll give more calculation details here as we go. So back to the question, what proportion of college students are parents? Well, that's P, and we don't know that and can't know that very practically. So we do a survey, and suppose that we want an 85% confidence interval. What we're going to do is we're going to compute our point estimate by dividing the yes by the total, finding out that 28% said yes to the survey, and that P hat is our point estimate. We then take that point estimate and we want to build an 85% confidence interval around it. In other words, we want to take the 28% and add and subtract a certain number, creating a process that will capture the true population proportion 85% of the time. So we compute our standard error as discussed before, which in this case is 2%. And again, we want to know these purple distances, but to know them, we have to know how many standard errors that each one represents. And in a previous picture, it looked to be about 1.5 standard errors. And I mentioned offhandedly that it turned out to be 1.4. Well, let's examine this idea. We can find the number of standard errors by using the inverse norm function that's included in most softwares, and in particular on graphing calculators. And you've seen if you've gotten this far in statistics, you've seen inverse norm before. Let's examine a little bit more about where all of this came from. This number here is your confidence. And what you can see in this diagram is a bell curve broken up where the yellow section is the lower half or 50% of the bell curve. What's currently the green section is half of our 85% confidence. And you may recall that an inverse norm gives us the number of standard deviations, also known as the z-score, to the right of whatever area we put into it. In other words, if we add the yellow and green areas together and get 0.92 and we pass that along to inverse norm, it will give us the z-score of the boundary between the green and the red, which is the number of standard errors above the center that we've been looking for this whole time, in this case 1.44. So what that means is, to make an 85% confidence interval, I need to be within 1.44 standard errors of my point estimate. By the way, we call this number a critical value. So to get our margin of error, which is essentially the length of either of these purple arrows, or the distance between our point estimate and the ends of our confidence interval, we simply have to multiply the critical value times the standard error. And this makes sense when you think about it, because we know that our standard error is 2%, and we know that we want to be within 1.44 standard errors of the center, so multiplying those together gives us our margin of error, or in this case 2.9%. Now that margin of error again is the length of this purple arrow, and so to get the right end of my confidence interval, I'll just do 0.28 plus my margin of error. And that gives me the upper end of my confidence interval. On the other end, the margin of error could be our point estimate minus that value, which would give us the left end point of our confidence interval. And ultimately, what these numbers in red are telling us is that while our sample may have produced 28% saying, yes, I have a child, yes, I'm a parent, the true population proportion is likely to be somewhere between the margin of error lower than that and the margin of error above that. In other words, between 27.1 and 30.9%. And that confidence interval statement is the final answer to this problem. Let me just take a moment to summarize the process one more time. Let's talk in more general terms. Suppose that we want to estimate a population proportion, but we can't obviously survey the entire population, assuming it's large, which is generally what populations are. And suppose we want to make a statement with a certain confidence level C. We do a survey, we compute the point estimate, p hat, the proportion who said yes to our survey, and we're going to build a confidence interval to the left and right of that point estimate, p hat. We compute the standard error, we compute the critical value based on our confidence, we multiply those together to get the margin of error. This margin of error represents a likely window of how far off our point estimate could possibly be from the true population proportion, and therefore we subtract and add our margin of error to our point estimate and make the final statement that the true population proportion is somewhere between the lower and upper ends of our confidence interval. And that concludes the lesson.